Welcome to video number 16 in the Using iTrain tutorial series. My name is Bob. In this tutorial we show how to prepare a locomotive for use in iTrain. Welcome back. We're going to perform this tutorial a little differently this time. We're going to use a video produced by Ian Morrison, and what you see here is a video of Ian's iTrain screen. We have the overview panel here, and down here we have the control grid with just one loco in it, showing Ian's cute little Weimar rail bus. And on the switchboard over here we show a portion of Ian's track layout. This section of track here shows a single block with 3 feedback sensors located in it. Ian uses this single block with the 3 feedback sensors to perform the speed measurements, which you will see later in the tutorial. To prepare a locomotive successfully, we need to follow a number of steps. So let's have a look at those steps and see what we're doing and why before we dive straight in. So why are we doing this? Well, the objective here is to prepare a locomotive for use in iTrain so that our trains move realistically and stop accurately each and every time. And we need to follow this process for every locomotive that we use in iTrain. Step 1 is creating a CV table. Part of the process that we are going to follow here requires us to change some CV values in the loco's decoder. There are 2 ways that we can change a CV value depending on which iTrain license you have. If you have the light or standard version, you will change the CVs externally to iTrain, either using your command station or a handset or a computer program such as the decoder manufacturer's own software, or Decoder Pro, which is part of the JMRI suite of software. If you have the Plus or Professional version of iTrain, you can use iTrain's decoder programming feature, and that is what we will be using in this tutorial. And to be able to use iTrain's decoder programming feature, we first need to create what's called a CV table, which allows iTrain to read and write to the loco's decoder. So if you have iTrain Lite or Standard, you can skip step 1 and go straight to step 2. In step 2 we set the CVs. And first we will change CV3, which is the acceleration CV, and CV4, which is the deceleration CV. We will change them both to 0. We do that to effectively disable the decoder's inertia simulation, because we're going to replace that with iTrain's own inertia simulation later in the steps. We'll then measure and set CV5, which is the maximum speed, and CV2, which is the minimum speed. This is to ensure that we have prototypical max speeds and to allow us to make use of the full range of decoder steps that are available to us, and not to waste decoder steps on speeds that are not appropriate to the model. In step 3 we create the speed profile so that iTrain moves smoothly and realistically at all speeds. In step 4 we set iTrain's own inertia simulation so that iTrain is now providing the realistic control of the loco. And finally, in step 5, we adjust the reaction delay, which allows us to fine-tune the stopping position of the loco. So again, you can skip this step if you have the light or standard version of iTrain. What we're going to do is create a CV table which will allow us to use iTrain's decoder programming feature to read and write CVs to the loco's decoder. Before we can use the decoder programming feature to read and write anything to the decoder, we first need to define the decoder's configuration so that iTrain knows what it is reading and writing. There is no read all values, as this would take a long time on a service track especially, and we would not know how to interpret the values. In iTrain's locomotive properties, there's a tab called Configuration, and this is where we define the decoder's configuration. What we need first, of course, is a locomotive with a DCC decoder in it, and place it on our track so that we can access the decoder. We open the locomotive properties by going up to the edit menu or pressing Ctrl F2. Or another way to do it is to double click on the train in the overview panel, and that will show the train in the first throttle window here. Then click on the locomotive tab and double click on the image to show the properties window. In the configuration tab, the table is blank and we need to define the list of CVs that we want iTrain to read and write to. There's two ways we can populate the list. We can right click and select DCC default, which shows the standard NMRA mandated CVs. To see just the CVs that are in use, double click on the use or number column and double click again to reveal them all. We can change the description of any of these by double clicking on it, entering a comment and then clicking OK. And if we open again, we can see the comment is saved. The other way you can populate the list is by creating your own template. And this is particularly useful if you use the same type of decoders. Here Ian's previously created an ordinary locomotive properties file called Zemo default set. You just open the file, tick all the CVs that you want to read and write to, select the type of CV and then enter a description in the comments. Here you can see that Ian has used the Zemo user guide to tick all of the CVs that he thinks he might want to read and write to. Then selected a type and entered a description. And then we copy them to the other loco by selecting Ctrl A to select them all and then right click and copy. Then we can go back to the other loco, double click on it in the overview, click on the locomotive tab, double click the image to open the properties. Click on row 1, right click and paste. And as you can see, that has now copied over all of those decoder values, and we can press OK to save. So now we can change the CVs using iTrain's programmer, which we open from the View menu. And if you don't have this option, you'll use whatever means you normally use to change CVs, like your command station, handset or external software. Here we'll use the programmer and click on Locomotive. So here we have the CV table that we created earlier, and we can now use it to read the values from the decoder. Now we can either place our loco on the service track and select the service track option and then highlight all the values that we want to read in, and then press the read button, and that will read all the values into our table. Or if you have a Railcom decoder, which Ian does, as seen by the red square here, we can leave the loco on the main track, press program on main, and then click the read button to read all the values into the table, and then press apply to save it into the iTrain database. Now we can see here that the acceleration CV3 and the deceleration CV4 are already at 0, so there's no need to change those. But the maximum speed CV5 and minimum speed CV2 both need to be changed, so we will do that. Now we want to ensure that the maximum speed is set at a prototypical value for this loco, and Ian has done his research and seen that for this model it's about 50 kilometers per hour. Now we actually want to measure what the maximum speed is, so we go up to the view menu, down to speed measurement, and then to locomotive, and then select the loco from the drop down menu. Now here we talk about speed measurement methods, which we will cover in a separate video. Ian's using the center feedback method and has a measuring area of just over a meter, 100.4 centimeters. We're going to measure just the maximum speed for now. So we select the max speed only and press start. Now if on your layout the loco shoots off in the wrong direction, simply press the stop button and then direction and then start, and it will start it again in the other direction. Right, so the measurement has come back as 86.4 kilometers per hour, which is far too fast for this type of loco. The real loco doesn't travel anywhere near that speed, so it would be unrealistic to keep it. So we need to change CV5, and we'll try an initial setting of 130 and see what that does. So we type it in and then click write, which we can do with or without a Railcom decoder. We can write to any decoder and leave it on the main track. And then we click apply, which writes it back to the iTrain database. We then measure the maximum speed again and see if we are nearer to the 50 kilometers per hour. It's a bit too high, so we'll alter the value again, and this time try 110. We'll click on write and then press apply, and we'll press start to start the measurement again and see what value it comes out at this time. And we get a measurement of 51, which is pretty much spot on. So that replicates the speed of the loco in real life. For minimum speed, we'll set it to something that's equivalent to a brisk walking pace, because this will help the loco move each time. Now Ian is already familiar with this loco, and he knows that a good value for this is 28. So we'll type that in now. Click write to write the value to the decoder, and then apply to save the value to our table here. We then scroll to speed step 1, select it, and then press the start button to measure it. This measurement will take quite a bit longer to complete because it's moving at a slower speed, of course. But that measurement is now complete, and we've got a value of 3.6 kilometers per hour at the lower end, and at the upper end we have that value of 51 kilometers per hour, which is absolutely perfect. Now we're going to perform the full speed profile. We'll press clear to give ourselves a clean page. And this time it's very important to select use direction specific measurements, because all locos perform differently moving forwards to moving backwards, and that is very important. This next bit will save us a lot of time. On this panel where the speed measurements are actually done, right click and choose Select with Step 5. This will then reduce the amount of measurements to every 5th speed step. iTrain will then perform the measurements and fill in the gaps, which allows it to draw a very smooth speed curve on the chart. We then press Start to begin the automatic measurement process. The loco will then start moving forwards or backwards depending on how it was last operated. On the track here we can follow the progress of the loco as it moves, and you'll notice the red square with the loco's address written in it, and this shows that Ian's train has got a Railcom decoder fitted to it. If you don't have a Railcom decoder, you'll just see the usual red rectangle of the feedback sensor light up as it progresses across. We'll let that continue and come back after a little tea break. Well, there you go. It's finished the measurements. It's measured every 5th step, and now we've got a lovely clean curve all the way across the chart here. The gaps in the measurements that we can see here will be filled in by iTrain when we press the apply button. So we'll then have a speed value for every speed step when we click apply. And there we are, every step is now filled in. Now you might ask, why go to all the bother of limiting the top speed to the prototypical speed of the loco and the bottom speed to a few kilometers per hour? There are a couple of reasons for that. The first is that whilst the train is running, iTrain now has the full range of 126 speed steps to control the train. If you didn't limit the top speed, it may be that you end up with only the bottom half to use. Or if we didn't set the lowest speed correctly, the train may not start moving until we get to step 25, say. So you could end up not starting before speed step 25 or 30, and then maybe you will have used all the usable speed steps by the time you get to 90. So you end up having only 60 usable speed steps instead of the full 126. And the loco would not accelerate and decelerate as smoothly as it can. The other reason why you want to set the lowest speed step to around 3 to 4 kilometers per hour is that when you are coupling or decoupling a train in iTrain to split a loco off from a train or to connect a loco onto a train, it uses speed step 1. So if speed step 1 is set too low, it will never reach there, or if it's set too high, it will just smash into the train. So a speed of 3 to 4 kilometers per hour is an ideal speed to have. So that's why we set those max and minimum speeds. So having pressed the apply button, we can now close down this window and this window. Click the Loco tab and double click the image and click on the Speed tab. We'll see a very nice speed curve. Now it may be that the upper speed is higher than you want it to be, in which case we can use this box down here to type in what we want the maximum speed to be, say 50, and that will then restrict the train from going above that speed. If you had something like a steam engine, for example, where the forward speed was say 150 kilometers per hour, but the backward speed is something like 30 kilometers per hour, you can enter the backward speed here. If the speeds are the same in forward and reverse, then it will just be displayed as it's shown here. For the next step, we select the Options tab, where we have the inertia simulation, feedback offset and reaction delay settings. It's very important that we set the acceleration and braking before we adjust the reaction delay. Otherwise, the setup will not work properly. For both step delays, values of between 150 and 300 milliseconds are good values to use. The step size setting will depend on the number of steps that the decoder has. If it's a 14-step or 28-step decoder, then we use a step size of 1. If it's a 126 or 128 step decoder, then a step size of 3 to 4 is about right. For this particular loco, we'll start with a step size of 3 for the acceleration. And initially we'll use a step delay of 200 milliseconds, and we'll do the same for braking with a step size of 4. If we wanted the loco to accelerate a little slower, we could increase this value to 250 milliseconds, which would give it a gentler acceleration, which is perhaps more appropriate to this gauge of model that we're using, which is HOE. Polarity is set to unknown as opposed to normal or inverted because we're using a Railcom decoder. With a Railcom decoder, Railcom provides the direction information. Next, we will set the occupancy feedback offset. This is the distance from the centre of the front couplings to the first set of pickup wheels that are drawing current. And we need to do a similar measurement from the rear couplings to the first pickup wheels. You may recall this diagram from tutorial number 14, where we went into the feedback offset in more detail. For this Weimar Railbus loco, you can see from the image that the offset is the same for both front and rear pickup wheels. So now we're all set to perform the reaction delay adjustment. And that's the subject of our next video. So hope to see you then. Take care.